Artificial intelligence is transforming nearly every industry, but behind every AI model, cloud service, and digital platform lies a hidden dependency: electricity. Modern data centers operate around the clock, processing billions of calculations every second, and even a brief interruption can affect businesses, governments, and millions of users worldwide. As electricity demand continues to grow, ensuring reliable power has become one of the biggest engineering challenges of our time. This is where hydrogen fuel cells are beginning to change the conversation, offering a cleaner and more resilient way to keep critical infrastructure running when uninterrupted power matters most. The solution begins with a hydrogen fuel cell system. Unlike traditional backup generators that rely on combustion, a fuel cell produces electricity through an electrochemical reaction between hydrogen and oxygen. As long as hydrogen fuel is available, the system continues generating clean, dependable power with water and heat as its primary byproducts. Modern installations combine fuel cell modules, hydrogen storage, power electronics, cooling equipment, and intelligent controls into a single integrated system capable of supporting large electrical loads. Designed for continuous operation, these systems are becoming an increasingly attractive alternative for facilities where reliability, efficiency, and lower emissions are equally important. For decades, diesel generators have been the standard solution for emergency backup power. They are proven and dependable, but they also produce emissions, generate significant noise, require regular maintenance, and depend on fuel deliveries during emergencies. Hydrogen fuel cells approach the problem differently. Because electricity is produced electrochemically instead of through combustion, they operate quietly while eliminating local carbon emissions and reducing maintenance requirements. As organizations pursue sustainability goals alongside operational resilience, hydrogen provides an opportunity to modernize backup power without compromising reliability. Rather than replacing every existing generator overnight, fuel cells are gradually becoming part of a diversified energy strategy that prepares critical infrastructure for the future. Reliable electricity extends far beyond data centers. Hospitals depend on continuous power for life support equipment and emergency care. Telecommunications networks keep emergency services and communities connected during natural disasters. Airports require electricity for navigation, security, baggage systems, and passenger operations, while government and emergency response facilities must remain operational regardless of conditions affecting the electrical grid. Although these sectors serve very different purposes, they all share the same requirement: uninterrupted power. Hydrogen fuel cells provide a common solution that can be scaled to meet a wide range of applications, delivering dependable electricity while supporting cleaner energy objectives. In the next section, we move inside the system itself to understand exactly how hydrogen fuel cells generate electricity and why they are becoming such an important technology. Now that we've seen where hydrogen fuel cells are being deployed, let's look inside the system itself. At the center of the installation is the fuel cell module, surrounded by hydrogen storage, cooling equipment, power electronics, and sophisticated control systems. Every component has a specific role working together to convert hydrogen into reliable electricity. Unlike a diesel generator, there are no pistons, crankshafts, or combustion chambers producing power. Instead, electricity is generated through carefully controlled electrochemical reactions. This modular design allows multiple fuel cell units to operate together, enabling the system to grow as power requirements increase. Whether supporting a single telecommunications site or a multi-megawatt AI data center, the overall operating principle remains the same. Understanding these components provides the foundation for seeing how hydrogen is transformed into usable electrical energy. Every fuel cell system begins with a reliable supply of hydrogen. The storage vessels shown here safely contain compressed hydrogen at high pressure, ensuring that fuel is immediately available whenever electricity is required. Pressure regulators reduce the hydrogen to the precise operating conditions needed by the fuel cell stack, while valves, sensors, and automated safety systems continuously monitor flow, temperature, and pressure throughout the installation. Unlike diesel storage tanks that require pumps and liquid fuel handling, hydrogen storage is designed for controlled gas delivery with multiple layers of engineering protection. The amount of hydrogen stored directly determines how long the system can continue operating during an outage, making storage capacity a critical design consideration. Together, these storage systems form the fuel reserve that enables hydrogen fuel cells to provide dependable backup power for extended periods without relying on the electrical grid. Once hydrogen enters the fuel cell stack, the process of generating electricity begins. Inside each cell, hydrogen molecules are separated into protons and electrons by a catalyst. The electrons cannot pass through the membrane, so they travel through an external electrical circuit, creating the flow of electricity that powers buildings and equipment. At the same time, the protons pass through the membrane to the opposite side of the cell, where they combine with oxygen drawn from the surrounding air and reunite with the returning electrons. The result is a continuous electrochemical reaction that produces electricity, water, and a small amount of heat. Because this process involves no combustion, there are no flames, smoke, or local carbon emissions, making hydrogen fuel cells one of the cleanest methods of generating dependable electrical power. While the fuel cell stack generates electricity, many supporting systems ensure the installation operates safely and efficiently. Cooling equipment removes excess heat, maintaining the temperature required for optimal performance. Power electronics convert the direct current produced by the fuel cell into alternating current that can be used by buildings or supplied to the electrical grid. Air management systems provide the oxygen needed for the electrochemical reaction, while digital controllers continuously balance fuel flow, electrical demand, and operating conditions. Every subsystem communicates with the central control platform, allowing the entire installation to respond automatically as power requirements change. The result is an integrated energy system capable of delivering reliable electricity with minimal operator intervention, even during extended periods of continuous operation. When all of these individual components are connected together, they form a complete hydrogen power plant. Hydrogen storage supplies the fuel cell converts chemical energy into electricity, cooling systems maintain efficient operation, power electronics condition, the electrical output and intelligent controls coordinate every stage of the process. The modular nature of the system allows engineers to increase generating capacity simply by adding additional fuel cell units, providing exceptional flexibility as facilities expand. This architecture also improves reliability because individual modules can continue operating even while maintenance is performed on others. Rather than functioning as a single machine, the installation operates as an integrated energy ecosystem designed to provide continuous, resilient electricity for critical infrastructure whenever conventional power sources become unavailable. Modern hydrogen fuel cell systems are managed by advanced digital control platforms that monitor every aspect of system performance in real time. Thousands of data points, including hydrogen pressure, stack temperature, electrical output, cooling performance, airflow, and equipment status, are continuously analyzed to maximize efficiency and maintain safe operation. If electrical demand suddenly increases, the control system automatically adjusts hydrogen flow and power production within seconds. Predictive diagnostics can identify potential maintenance needs before failures occur, improving reliability while reducing operating costs. Remote monitoring also allows operators to supervise multiple installations from centralized control centers, ensuring consistent performance across large fleets of fuel cell systems. With intelligent automation coordinating every component, hydrogen fuel cells become more than clean power generators. They become smart energy assets ready to support the increasingly complex electrical infrastructure of the future. With the technology understood, we can now see where hydrogen fuel cells deliver the greatest value. One of the fastest growing applications is the AI data center. These facilities consume enormous amounts of electricity while processing cloud services, artificial intelligence models, financial transactions, and digital communications around the clock. Even a few seconds of power loss can interrupt critical operations, corrupt data, and cost millions of dollars. Hydrogen fuel cells provide continuous backup electricity without the noise and emissions associated with conventional diesel generators. Operating alongside batteries and uninterruptible power supplies, they extend backup duration and improve overall resilience. As AI infrastructure continues expanding worldwide, hydrogen is becoming an increasingly attractive solution for ensuring these digital facilities remain online under virtually any operating condition. Beyond data centers, telecommunications networks form another essential layer of modern infrastructure. Mobile phone towers, internet exchanges, fiber optic networks, and emergency communication systems all depend on reliable electricity to keep people connected. During hurricanes, storms, or widespread power outages, communication networks often become even more important than under normal conditions. Hydrogen fuel cells can provide extended backup power without frequent refueling, allowing telecom sites to remain operational long after batteries have been depleted. Their compact footprint, quiet operation, and low maintenance requirements make them particularly well suited for both urban installations and remote communication sites, where dependable electricity is essential for public safety and emergency response. Hospitals represent one of the most demanding applications for resilient power because lives depend on uninterrupted electricity. Operating rooms, intensive care units, medical imaging equipment, laboratory systems, refrigeration for medicines, and life support equipment must continue functioning regardless of external conditions. While diesel generators have traditionally served this role, hydrogen fuel cells provide an alternative capable of delivering clean, quiet, and dependable electricity during extended outages. Reduced emissions also improve air quality around healthcare facilities, while lower noise levels create a more suitable environment for patients and medical staff. As hospitals pursue both resilience and sustainability, hydrogen fuel cells are becoming an increasingly important part of modern healthcare infrastructure. Airports operate as highly integrated electrical systems where almost every activity depends on reliable power. Airfield lighting, navigation equipment, radar systems, passenger terminals, baggage handling, security screening, and communication networks must all function continuously to ensure safe operations. A prolonged power outage can disrupt thousands of passengers and affect flight schedules across entire regions. Hydrogen fuel cells provide airports with resilient backup electricity capable of supporting critical systems while reducing emissions associated with conventional generators. Their modular design also allows airport operators to expand capacity as terminals grow and passenger numbers increase, supporting both operational reliability and long-term sustainability objectives. Government facilities, emergency response centers, military installations, and other secure sites require power systems that remain operational under the most challenging conditions. These facilities often coordinate disaster response, public safety, national security, and essential government services that cannot tolerate extended electrical interruptions. Hydrogen fuel cells strengthen resilience by providing independent electricity that continues operating even when the surrounding electrical grid is compromised. Combined with renewable energy and battery storage, they create diversified energy systems capable of supporting critical missions during emergencies. As governments invest in more resilient infrastructure, hydrogen is increasingly viewed as a strategic technology for strengthening both energy security and operational readiness. Although these applications appear very different, from AI data centers and hospitals to airports and secure facilities, they all depend on the same underlying technology. Hydrogen fuel cells provide clean, scalable, and reliable electricity wherever uninterrupted power is essential. Their modular design allows systems to be tailored for individual buildings or expanded into multi-megawatt installations, supporting entire campuses and industrial complexes. Rather than replacing existing technologies, fuel cells are increasingly working alongside batteries, renewable energy, and conventional backup systems to create more resilient energy solutions. In the next section, we will expand beyond individual facilities to explore how hydrogen contributes to strengthening electrical grids, integrating renewable energy, and building a more flexible and reliable power system for the future. The value of hydrogen extends beyond individual buildings because it can strengthen the entire electrical grid. As renewable energy continues expanding, utilities must balance electricity supply and demand despite changing weather conditions. Wind speeds fluctuate, clouds reduce solar generation, and electricity demand rises and falls throughout the day. Hydrogen provides a way to store excess renewable electricity when production is high and convert it back into power whenever additional generation is needed. Instead of allowing valuable renewable energy to go unused, it becomes a flexible energy reserve that supports grid stability. This ability to store energy for extended periods makes hydrogen an important complement to batteries, helping utilities build more resilient and reliable electricity systems. The journey begins with renewable electricity. Wind farms, solar parks, hydroelectric facilities, and other clean energy sources generate electricity that can either be supplied directly to the grid or used to power electrolyzers. These electrolyzers split water into hydrogen and oxygen using electricity. effectively converting electrical energy into chemical energy. The hydrogen can then be compressed and stored until it is needed. When electricity demand increases or renewable generation declines, that stored hydrogen is supplied to fuel cells, which convert it back into electricity. This process creates a complete renewable energy cycle, allowing clean electricity generated today to be used hours, days, or even weeks later when the grid requires additional power. One of hydrogen's greatest strengths is its ability to provide long-duration energy storage. Batteries respond almost instantly and are highly effective for short-term fluctuations, but supplying electricity for many hours or several days often requires much larger storage systems. Hydrogen approaches the challenge differently by storing energy as fuel rather than electricity. Increasing storage duration simply requires additional hydrogen storage capacity, allowing systems to support extended outages without dramatically increasing equipment complexity. This makes hydrogen particularly valuable for critical infrastructure, remote facilities, and regions where renewable generation varies significantly over time. Together, batteries and hydrogen create complementary solutions that improve the resilience and flexibility of modern electrical networks. Building a hydrogen-powered energy system requires much more than fuel cells alone. Hydrogen production facilities, storage terminals, compression equipment, transportation networks, pipelines, refueling stations, and digital control systems all work together as part of an integrated infrastructure. Each component supports the others, creating a complete value chain from renewable electricity to final power generation. Around the world, governments and private companies are investing heavily in this infrastructure to support industrial decarbonization, transportation, energy security, and resilient electricity supplies. As these investments continue, hydrogen is evolving from individual demonstration projects into a globally connected energy ecosystem capable of supporting a wide range of industries. The transition toward hydrogen is already underway. Utilities, technology companies, industrial manufacturers, airports, hospitals, and governments are deploying fuel cell systems to strengthen resilience while supporting long-term sustainability goals. At the same time, continued investment is reducing costs, improving efficiency, and expanding hydrogen production capacity around the world. Although challenges remain, the technology has moved well beyond the research stage and is increasingly being deployed in real-world applications, where reliable electricity is essential. In the final section, we will look ahead to the future of hydrogen fuel cells and examine how they are expected to become an increasingly important part of tomorrow's clean, resilient, and intelligent energy infrastructure. The future of resilient energy will not depend on a single technology, but on intelligent systems that combine multiple solutions. Renewable energy will generate clean electricity whenever the wind blows or the sun shines, batteries will respond instantly to short-term fluctuations, and hydrogen fuel cells will provide dependable electricity during extended outages or periods of high demand. Working together, these technologies create an energy system that is cleaner, more flexible, and significantly more resilient than traditional power networks. Instead of replacing one technology with another, the future grid will integrate them into a coordinated ecosystem where each performs the role it is best suited to deliver. As hydrogen infrastructure expands, its influence will extend far beyond backup power. Production facilities, storage terminals, pipelines, transportation networks, ports, and industrial users are gradually forming an interconnected hydrogen economy capable of supporting multiple sectors simultaneously. Electricity generation, heavy industry, transportation, aviation, shipping, and digital infrastructure will increasingly share the same hydrogen supply chains. Every new investment strengthens this growing ecosystem, reducing costs while improving accessibility and reliability. What began as individual demonstration projects is steadily evolving into a global energy network that supports cleaner electricity, stronger energy security, and greater resilience across critical infrastructure. Hydrogen fuel cells are no longer simply an emerging technology. They are becoming practical engineering solutions for some of the world's most demanding power applications. Continued improvements in fuel cell efficiency, hydrogen production, storage technologies, and digital control systems are making deployments larger, smarter, and more cost-effective. As governments and industries pursue net zero objectives while preparing for increasing electricity demand, hydrogen offers a pathway that combines sustainability with operational reliability. Every successful installation demonstrates how clean energy and resilient infrastructure can work together to support the next generation of critical facilities. The future of energy is not defined by a single breakthrough, but by how multiple technologies work together to keep the world running. Hydrogen fuel cells are becoming an essential part of that future, providing clean, reliable electricity for AI data centers, hospitals, telecommunications networks, airports, government facilities, and countless other critical operations. As renewable energy continues to expand and global electricity demand accelerates, resilient power solutions will become increasingly important. Hydrogen is helping to build that future today, one fuel cell, one facility, and one integrated energy system at a time. Thank you for watching, and if you'd like to explore more engineering insights into hydrogen technologies and the systems shaping our energy future, visit H2 Hub by Renee Energy.